our model of Cal in the Jeep playing the saxophone. Okay, and as the car, this is the marker, this is me. As the car goes past, passes the observer, the waves in the front of the Jeep are shorter in wavelength, and that registers as a pitch change, and so we hear a lower or a higher pitch, and then as the car goes past, you hear the same pitch, and then at the behind the car, the waves are more spread out, and so that registers as a lower pitch, and so it's like wow.
So here we have the equation for the Doppler effect, which is the frequency the observer hears equals the frequency of the source multiplied by 1 plus or minus the velocity of the observer over the speed of sound, all that over 1 minus or plus the velocity of the source divided by the speed of sound.
And we calculated the speed of sound to be 331 meters a second because it's 0 degrees outside.
Here we have the velocity of the observer, which is Joey holding the camera, which is 0 meters per second because he is standing still.
And the velocity of the source is 8.7 meters a second because we dimensionally analyzed this 15 miles an hour, which Jess was traveling at.
And here we have the frequency of the source, which is 466.16 hertz, which we looked up on the internet to be because I was playing a B flat in the 4th octave. Now we're plugging numbers into our equation. We've plugged in the frequency of the source, the velocity of the observer, the velocity of the source, and the speed of sound. It's a 1 on top just because the observer isn't moving, so it's 1 plus or minus 0, so it will just come out to be 1 either way. On the bottom we have 1 minus the velocity of the source divided by the speed of sound, because no matter what that number ends up to be, it'll be less than 1. So as the the denominator goes down, the value of the whole fraction will go up. We ended up, after we multiplied it by the frequency of the source, to be 456.8 hertz, which makes sense because it is greater than the frequency of the source, and it is approaching us, so it should be higher than the actual value.
And then for going away, we want it to be lower, so it makes sense that this is 447.9 hertz. But to get that, we use this same equation. Got 0 for the top because Joey still isn't moving. We plug 0 in for the velocity of the observer, which gives us 1 on the top. And then below that we have 1 plus the velocity of the source, which is 6.71 meters per second, over speed of sound, which is 331 meters per second, and multiply that by the frequency of sound of the source to get 466.16 hertz. And then when you plug that into your calculator, the frequency the observer hears is 447.9 hertz.
Me? Oh, do I start? Okay. These are our plugged-in stuff. You ready?
Yeah, I'm recording.
Okay. We're plugging in numbers now. Is that good? Sound into our equation. And, okay.
Oh my gosh. And if you fall, you're totally falling on one of those wood stakes and can like go through your heart.
Oh my gosh!
Got this.